Hey there, and welcome to week 3. This week is all about logs and exponentials. So let's get started. Section 4.2, exponential functions. So you want to know what the graphs of y equals a to the x look like and y equals a to the negative x. In general, if a is greater than 1, y equals a to the x looks like this. And so in particular, y equals e to the x, which we use a lot in calculus, looks basically like that. And then y equals a to the negative x is just the reflection about the y-axis of that first graph. Notice that each function is always positive. And then you want to graph horizontal and vertical shifts of those functions using basic shifting techniques from the first week, and then solve some simple equation using the one-to-one properties of exponentials. Now, there are no videos about this in the video lessons, but there are some videos attached to each homework problem. The one-to-one property says that if you have the same base, like 7 to the 2x plus 1 equals 7 to the x minus 4, so if m to the a equals m to the b, then that means that a equals b. If the bases are the same, you can just set the exponents equal. So you would solve this by setting 2x plus 1 equal to x minus 4, and then solving that. Section 4.3, logarithmic functions. Video 1 talks about converting between logarithmic and exponential equations. So in a nutshell, here's the relationship. Y equals log base a of x, log base a of x equals y if and only if, that's what the double arrow means, if and only if a to the y equals x. So you want to be able to write each equation in exponential form as a logarithmic equation and vice versa. Common log is log base 10. So if it's log base 10, we just write log x. And then natural log is log base e, and we write ln x. We don't write log base e, we just write ln of x. That's the one we use in calculus the most. Evaluate logs without a calculator, and the way you do that is take the logarithmic equation and rewrite it as an exponential equation, and videos 2 through 6 walk you through that. Properties of logs we're going to talk more about in section 4.5, but I'm going to just explain them here in this box, and this is something you do need to memorize. There's not a lot you need to memorize, but there's certain things you need to memorize in math, kind of like you know your address and you know your name. These are things you need to know. So algebraic properties, I'm going to state them all in terms of natural log because this is the one we use the most often. And in Calc 1, usually what I do is start the first week with just a review of properties of logarithms. So let's go through this. Ln of a product, x times y, is, sorry about that, ln x plus ln y. It's the sum of the logarithms. Ln of a quotient is the difference of the logarithms, ln x minus ln y. Ln of x to the r, that r, which is an exponent, can come down as a coefficient. That's a great property. The inverse properties tell us that if we have e to the ln x, then since exponentiation with base e and natural log are inverse functions, this just gives us x back. And it goes in the other direction too. Ln of e to the x is x. And the change of base formula, log base a of x, I'm just going to change it over to natural log, ln x over ln a. Now, why is this one important? If you look at your calculator, you will not, if you have a calculator, you will not see like log base 2 on that calculator. So if you wanted to evaluate log base 2, let's say, of 5, you could not do that on a handheld calculator. You'd have to rewrite it as ln of 5 over ln of 2, and then you could punch those into your calculator. All right, graphs and domains of logarithmic functions. So the graphs, you should know the basic graph of y equals ln x. Notice that it's only defined for positive values of x. And the domains, here's what I really want to talk about. Your domain videos show you an alternate way to find domains. I want to just show you my way, which I think is preferable. If you want the domain of y equals ln of any function f of x, and this works for any log. So this is, I'm doing for natural log, but this is the same rule for log base 2, common log, any log. The domain of this is found by setting f of x greater than 0, because the natural log is only defined for positive values. So it just makes it very simple. You just take the argument of the natural log out, set it greater than 0, and then solve. Okay, section 4.5, that's properties of logarithms. We just talked about those. 4.6, exponential and logarithmic equations. So video 1 is an overview of solving logarithmic equations, and then video 2 is an overview of solving exponential equations using logarithms. And so I just want to point out two things about this section. One, when you're solving an equation involving logs, you always have to check your answer. And here's why. I'll just show you this quick example here. Suppose we want to solve ln x plus ln of x minus 2 equals ln of 5x. The first thing you want to do is rewrite the left-hand side using the properties of logarithms. So the left-hand side is going to be ln of x squared minus 2x. You take the product, and that's equal to ln of 5x. Now we can use the one-to-one property of logarithms, which tells us that if ln of m equals ln of n, then m equals n. So if you have a single log on both sides, you can just set the arguments equal. But first, you have to rewrite it so you have a single log on the left. So we can set x squared minus 2x equal to 5x. Now subtract 5x from both sides. X squared minus 7x is 0. Factor, moving over here, x times x minus 7 is 0. So seemingly we have two answers, x equals 0 and x equals 7. But we don't, because take a look at the original equation. It's not even defined when x is 0. You cannot take the logarithm of 0. You can only take logarithm. If you put in 7, you're good. You're good to go. Everything's defined. But this guy is no good, so you have to toss it out. All right, and the other thing I wanted to point out is that you're going to have to give your answers as exact answers in this section. But when you click on the little answer key to see the answer, you'll see the decimal approximation of the answer. There's no way around that. I'm sorry, I can't fix it. So for example, if you want to solve 4 to the x equals 50, here's how I would do it. Take the natural log of both sides. ln of 4 to the x is ln of 50. Now use the property of logs that exponents can come down as coefficients. X ln 4 is ln 50. So now divide both sides by ln 4. ln 50 over ln 4, there's your answer. If you put that into the answer box, you will get it correct. Now there's another way to do this that I don't like as much, but I want to show it to you. If you have 4 to the x equals 50, you could take log base 4 of both sides. So log base 4 of 4 to the x is log base 4 of 50. And then log base 4 of 4 to the anything is anything, because those are inverse functions. So that gives us x is log base 4 of 50. Well, that's okay, but if you have to send a person to the moon and you need a decimal approximation, the first thing you're going to have to do is rewrite that in terms of natural log, like that. So I prefer writing all my answers in terms of natural log. Okay, here we go. Last section. And again, there's memorization here that you need to do. And I apologize for that, but you should make some flashcards. Circles and the Pythagorean theorem. You might already know the Pythagorean theorem. Hopefully you do. A squared plus B squared is C squared for a right triangle. And the distance formula. So the distance between 2 points, you have to know that formula. And then video 3 is an overview of circles. So when you have a circle equation in this format, this equation describes a graph that has center HK and radius R. And what the trick is in this section is taking an equation that's not in standard form like this, completing the square and rewriting it so it looks like that. Because when I look at this equation, I say, well, I have no idea what the center and radius of that circle is, right? So you have to rewrite it. And so watch the videos on that and be able to do that. It's a big week. And that's the end of the summary.